In this unit, we're going to see how to graph polynomial functions. This is a very important unit, so make sure you understand the concepts illustrated here. Here is a fairly basic example. It's asking us to identify the leading coefficient, the degree, and the number of terms, three things, by a given function. Now, this function is given, the order is not right, so the first thing we need to do is to rewrite it into the right order. By right order, I mean I start with the highest degree, the term with the highest degree, and then it goes in descending order. Obviously, this is 1, and this is x raised to the 0, right? And so now you can tell the leading coefficient is 2, and my degree, my highest degree, is 3, and then the number of terms is also 3. So this is a cube function. Straightforward. Here is an important example. How do the sign of the leading coefficient and degree of a polynomial affect the end behavior of the graph of a polynomial function? So our focus here is the sign of the leading coefficient, and as well as the degree of the polynomial function. Okay, so let's see what we do here. So here are 4 different scenarios. Let's focus on the first one. If I have an odd degree, so cubed function, raised to the 5th, raised to the 131th power, so on and so forth. If the degree is odd and the leading coefficient is positive, what do you think is going to happen? So it's connected with one of the functions we're very familiar with, which is, if you look at this example here, it follows the behavior of f of x equals x, which is this red line. And here are 2 examples. The blue function is a cube function, and h of x has a power of 5, right? And they just take different turns at different times, but the general trend is f of x equals x. So it's not that hard at all. In this example, if I want to expand this slide, this first part, you will see that as x approaches infinity, my y approaches infinity. As x approaches negative infinity, y approaches negative infinity. Okay? Now, I want us to skip one and go to the third option, which is still odd degree, still the same function. I'm only going to change the leading coefficient to negative. So what's going to happen there? Let's see. I click on that. Look at that. It follows the behavior of f of x equals negative x. It follows this red line. It just flips everything, mirrors everything around the y-axis, obviously, right? Because its leading coefficient is negative. So now, what do you think the end behavior looks like? When x approaches positive x, that's your alarm for the class, actually. My y, what's happening to my y when x approaches positive x? Alexa, stop. When x approaches positive, y is going down, approaching the negative. When x approaches negative infinity, y is going up, approaching positive infinity. Okay, so that's fairly straightforward. So when you're given a cube function, for example, just think about how f of x behaves, and it follows that. By the same token, now let's evaluate even degrees. And as probably you can imagine, it follows the end behavior of f of x equals x squared, quadratic equation. Okay, so the red one is the parent function of quadratic equation. Here are two examples, and they both follow that. And the end behavior is as x approaches both positive and negative infinity, y approaches positive infinity. Look at that, both hands up. Now, if I take the leading coefficient and negate it, I still have an even function, but now look at the graph. It follows what f of x equals negative x squared, and therefore the end behavior also follows that. As x approaches positive and negative infinity, y approaches negative infinity. So it doesn't matter whatever highest degree I can give you in my example, you have to have this parent function of f of x equals x squared or f of x equals negative x squared in mind. Okay, looks like it's a lot of information on this slide, but if you really understand it, especially if you can graph it by hand very quickly, absorb it, it's going to come really helpful in the future. A lot of the application problems is based on your connection with this concept. Here's an example. It's asking us to graph this funky polynomial with the table method. So table method, you have to find hopefully some turning points, and then you get some numbers to the left of that turning point, and then to the right, right? But before we begin, notice that right here, the highest function is is 4, so it follows f of x equals x squared and behavior. The leading coefficient is negative, so this would be a sad face, right? So here, I did not do this by hand. So this is from your textbook. We start with 0, right? Because the indicator is it follows y equals f of x. So we start 0, we end up with a 2. Then we take some values north of 0 and some values south of 0 or less than 0. And then we have its corresponding values. And then if you graph it out, you notice that there's some intervals here. In this interval between 0 and 2, it's increasing. So the function will rise up. But then after 2, the function will decrease. Okay? Same thing over here. In this interval, it will decrease first, and then it will rise up later. So now you know that at least there's a turn there. And as we mentioned, that we expect this to follow the end behavior of f of x equals x squared. So both ends of the graph will trend towards negative infinity. So there you go. We plotted the 5 dots on the coordinates. And then as we said, that here gives us a turning point. It will rise in this interval, then fall. And then on the left-hand side, it will rise, and then it will fall. And both sides, both ends of that graph are going towards negative infinity. So it matches, it describes all the key feature of that polynomial function. It's not precise. If you graph it out in decimals, you will get a precise one, but this is good enough. Here is an example that links to Algebra 1, rate of change, or slope rather, right? So it says, here's the function, still the same function. How can you use the graph to estimate the average rate of change over the interval of -2 and 0? And if you recall, the average rate of change, if I want to write it out, is rise over, it's not y, it's m. It's my eraser. It's rise over run. And rise is the change in y, and then the run is the change in x, right? Actually, I should do, rather than doing that, I should do change in y over change in x. Therefore, That's why when we write it more intelligently, mathematically, we say the change in y, which is the first y value, subtract the second y value over the first x value, subtract by the second, or second minus first, second minus first, it doesn't really matter. So now we're given -2, 0. So you just plug it in. You plug in -2, you should end up with 6. Yeah, if you plug in 0, you should end up with 2, right, for the y value. So you just plug in this formula, you will end up with -2. And therefore, the average rate of change over the interval is, over the interval of -2 to 0 is -2. So again, a recap. To find rate of change in an interval, you have to understand that the formula you're looking for is the change in the y-axis over the change in the x-axis. Over here, the change in the x-axis is -2 to 0, so it's 2 units. But the change in the y, you have to plug in both -2 and 0 to solve for the change in y. And then you get the final answer there. Here's an example where we're not given a very specific function, but we're given a bunch of descriptions and lots of intervals. So don't be overwhelmed by it. Look at the focus of how these questions are given, right? It's really telling you in which direction that how these functions are going in those intervals. So in that case, I would graph out the intervals first. So let's look at, so first I'm going to identify the x-intercepts because that determines my interval. And that will give me, tell me that the signs in that, it tells me that the sign will change at that point, at these x-intercepts. Then the next step is I'm going to identify the turning points. Here it's telling me positive and negative. Is it yeah? Negative 2.67 and positive 2 are the places where they change signs. And so from that point, I know that. So for example, the function would change direction at x equals negative 2.67, and there's a relative minimum at that point, right? But then at x equals 2, there should be a maximum somewhere. Probably it's over here. It's that's what I'm anticipating at this moment. I don't know the exact behavior just yet. So now let's look at the AND behavior. Now it's telling me that when x is less than negative 2.67, the function f of x is decreasing, which means over here, as x goes towards negative infinity, y goes up, right? And also, when in this interval, when x is greater than 2, when x goes into positive infinity, y decreases accordingly. So my AND behavior there should look something like this. So finally, I already have this trend, right? This trend going this way, and I know there's a relative minimum right around, what did we say, right around -2, and then has to turn around and go up like that, and there's a relative maximum at x equals positive 2, and then it decreases that like that. So I have the general shape of that graph, and you just need to graph it out. And that's what this function looks like. So when you're not given a very specific function, you're given a bunch of descriptions of the behavior of the function. It's much easier if you focus on one interval at a time. Make sure you truly understand what does it mean when a function increases? What does it mean when a function decreases? Make sure you understand end behavior. Then you find these critical points where they turn, right? Where you can find the maximum and minimum, then you can sketch it out. I don't particularly like this example, but it does give you a practice of how to interpret polynomial models. So let's look at it. In science class, Abby mixes a fixed amount of baking soda with different amounts of vinegar in a bottle, capped by a balloon. She records the amount of time it takes the gases produced by the reaction to inflate the balloon. It sounds like a lot of fun, actually. From her data, Abby created a function to model the situation. For x quarter cups of vinegar, so pay attention, it's x quarter cups of vinegar, it takes this amount of time, which is this equation, in seconds, to inflate the balloon. So how long will it take to inflate the balloon with 5 quarter cups? So when x equals 5. Okay. It's a pretty straightforward question if we have all the information. We don't have the precise information. So in this case, you have to rely on your technology. Use your decimal or use your graphing calculator, plug it in, and plug the equation in, and you should have a graph that's looking like this, right? This is what it's telling you. So it's saying that you have to use your trace function, and now it's 5 quarter cups. So whatever the corresponding y value of 5, in this case it's 6.3 seconds. That's the answer to this question. Second question here, what does the x and y intercepts in the graph mean in this context? Do these values make sense? So what it means is that when x equals 6.585, y, which is the amount of time, is 0. So in other words, it takes no time. If she puts in 6.5 quarter cups of baking soda, it takes 0 seconds to inflate it. Obviously, that does not make sense. Let's look at the y-intercept. The y-intercept is approximately 13.2, which means that if no vinegar is used, the balloon will inflate in 13 seconds. Obviously, unless there's a ghost in the room or some kind of magic to be performed, that in reality is just not making sense. So we have to make sure to illustrate that when we talk about the domain and range, x cannot be 0 and y cannot be 0 in this example. That's it for this unit. We mainly focused on the relative minimum, relative maximum, and the turning points when we talk about intervals. And then we use the and behaviors. Just remember how they are correlated with f of x and f of x squared. All the polynomials goes back to these two parent functions when you discuss their and behaviors. So with these two blocks of information, you can analyze or sketch just about any polynomial functions, more or less. Okay?